So we're now going to begin discussing laws of logarithms. So just as we have our index laws, we also have log laws, and these are things that you need to commit to memory. The first one is called the addition of logs. So let's begin by looking at this before us. So we've got log of base a of m plus log of base a of n is equal to log of base a of what? So in order for this first one to work, what you need to ensure is that you've got the same bases. So here we've got the same bases of a. And in this situation, what you do when you're adding two logs of the same base is you multiply the arguments. So that means we're going to end up with mn, so m times n there. Okay, let's see how this operates in action here. So here's an example. Log of base 2 of 8 plus log of base 2 of 4 is equal to what? Well, you could answer these separately. You could say, well, what is log of base 2 of 8? Well, that's saying 2 raised to what power is equal to 8? We know it's going to be 3. Here, it's saying 2 raised to what power is equal to 4? We know that that's going to be 2. Then we could go 3 plus 2 is equal to 5. So that means we know that our answer to this question is going to be 5. But, that's a bit of a slow way to do it. It could be written also as the following. So we could also do it like this. So instead of, answering them both separately, we could have taken both the arguments and multiplied them together. So 8 times 4. Now we've got log of 2. Now what's 8 times 4? It's 32. Now we're asking the question, 2 raised to what power is equal to 32? Well, it's going to be 5. So do you see how we can do it a bit quicker by using our first log law? And that is our first log law. All right, let's now move on to our next one, which is about subtraction of logarithms. So take note again, this time we're subtracting two logs with the same base. And what we do in this scenario is we divide the arguments. So that means I take m and I divide it by n. Now let's go through this. If I was to do it the long way, so here I have an example of log base 2 of 16 minus log base 2 of 2. Well, this is saying 2 raised to what power of 16? Well, that's going to be 4. And this is saying 2 raised to what power is 2? Well, that has to be 1. So my answer is 3. So that's if I was to do it slowly. And as you can see, I kind of just treated each log separately. But if I was to do it quicker, what I would do is I would take the arguments and I would divide them by each other. So 16 divided by 2, which means I would end up with log 2 of 8. And what is log 2 of 8? Well, this is saying 2 raised to what power is 8? My answer will be 3. So as you can see, it's much quicker to use your log laws. All right, we move to another log law here. All right, this one is saying log of base a of m raised to the p is equal to what? Well, in this scenario, what you do is you take this p and you move it to the front. So now you've got p times log of base a m. All right, let's see this one in action again. So here's an example, log of 2 of 4 cubed. Now, if you were to do this the slow way, you would say, well, 4 cubed is the same as 64. And then you'd have to ask the question, 2 raised to what power is equal to 64? And after some thinking, you would say, well, that's going to be 6. But do you see how this is kind of tricky? Because you're going to end up with quite big numbers. So the better way to approach this is instead of going 4 cubed is equal to 64, instead take this 3 to the front. So now you've got 3 times log of base 2 of 4. Now, what is log 2 of 4? So 2 raised to the second power is going to be 4. So it's 3 times 2, which is equal to 6. Do you see how that's a lot easier than doing it this way? This way, you're going to get really big numbers. Using this log law about powers is far easier. All right, we keep on going here. Some other log laws that you need to know is that if I have log of base a of 1 on m, what you can do in this scenario is just make this -1 times log a of m. Now, why does this occur? Well, it happens for the same reason as this. We know another way to write this is log a. Now, if I take the reciprocal, I now have to change the sign of the power. So now it's this. And now you can just take that -1 to the front. So you're going to get -1 times log of a m. And that's why it works. And the same logic over here. So this one is log of base a of n on m, and this is going to be equal to -1 times log a of the reciprocal. So instead of n on m, now it's m on n. Now the reason why this occurs is because remember, when you take the reciprocal or swap the numerator and denominator, same thing, m on n, you have to change the sign. So now this is this. If I could put this all in brackets if I wanted to. And now you can take this negative to the front. So -1 log, and I'll put that times there, times log of a m on n. So that's the thinking behind what's going on there. All right, I think we have just one more for this part, and then I'll take a break. All right. The argument of one, an identical base argument. So these are ones that you two just need to keep stored away in your minds and always be thinking of them. If you're in a scenario in which you have an argument of one, you always know what the answer to that log is going to be. And it's going to be 0. And the thinking behind that is a raised to any number, a raised to what number will be equal to 1? Well, if it's equal to 1, it has to be 0 here. X has to be equal to 0. And that always occurs. Even if a was, it doesn't matter what a is. A could be 500, a million, whatever it is going to be, you're always going to end up with a power of 0 if your answer is 1. And then the last one here, not too tricky at all, a raised to what power is going to be equal to a? Well, x has to be equal to 1. And that makes sense because, to get the same answer as the base, the power has to be 1. There's just no way around that. All right, perfect. Hopefully all of that has made sense.